You've already heard a little bit in the talks yesterday and certainly today about multithreading. Geant4 was designed in the 1990s. Multithreading was not a hot topic at the time, and we'll get to why it became a hot topic. It has been put in about 10 years ago after extensive studies. So the reason that this became necessary, as you may or may not be aware, was about 20 years ago. Until about years ago or so, processors' frequency increased and performance increased every year, so that most people did not really need to worry about the performance of their application so much, because if they waited 6 months or 12 months, the CPU power that they could buy had already increased, so it was not as much of a consideration. Of course, large experiments which needed to buy thousands of CPUs nevertheless had to be concerned about it, but their purchasing power got more. However, when the power that was created that was consumed by a CPU and the heat that was generated around 2004 became significant enough that you could use it to cook a fairly interesting meal, it became impossible to continue to increase the frequency, and thus more cores. And the number of cores has been growing since then, even on desktop, or certainly on desktop, even on laptop. And thus, in order to utilize for almost any application the full power of any machine that you have at your disposal, and not to have to run a dozen instances of your application, having a multi-threaded application became of significant interest. So the CPU rate and core count has basically stopped in around 2002, 2004, and the core count has grown quite a bit since. I'm not suggesting that you can buy a laptop today with 256 cores. Nevertheless, it is not something that's unheard of in machines that exist in servers, and having machines with less than 8 cores is something that would be a surprising factor unless you bought the cheapest machine on offer. That means also, though, that the amount of memory that you have per core on your machine is an issue. If you want to simulate a complicated setup, for example, an LHC detector, between the geometry, the physics, the number of materials, the amount of memory that each time you're simulating utilizes is not an insignificant factor. The number of transistors, which has continued to almost double even since 2004 in your CPU, are now being utilized for the purposes of creating extra cores and, of course, for improving the memory hierarchy to feed them. So it has become necessary. We already recognized it in the late 2000s to introduce parallelism, and memory and the way it was accessed was at the top of our considerations. You could, of course, take an application and run it potentially with different parameters, hopefully with different random numbered seeds in each. If you had 8 cores, you could run 8 versions of your simulation. If you're wanting to run only one configuration, give different random number seeds to each of these and produce a fair amount of data. Where you could hit a brick wall is if each of these required more memory than you have available in your system. You have one major advantage in a Geant4 particle transport simulation, in that the events that you have are independent. You have to typically simulate thousands to tens of thousands, if not hundreds of thousands of events. So there's a very natural event level parallelism, and that's what we have exploited. Originally, the prototypes were done in the late 2000s, so 2007, 2008, 2009 or so. However, the first versions that were more widely distributed for testing were in the early 2010s, and we decided to re-engineer Geant4 and put it out there, rather not as a prototype, but as part of the main production release at the end of 2013. So we spent a fair amount of 2013 taking the prototype, embedding it in the code, and making sure that things worked reasonably well. Of course, things didn't work perfectly with the first release, and you will see a few of the things that have been improved since. But generally, let's go back and understand the concept. In a Geant4 single-threaded application, you will create a G4 run. You'll create any sort of application. When you have multiple copies, you could run the application by itself, and each of these would require a certain amount of memory. Instead, in a multi-threaded application, you'll have something that starts in single application, and then other threads will contribute to the work. In general, the initialization will be done in what we're calling the master thread, and the worker threads will be doing the event simulation. There's no magic wand. There is a fair amount of memory sharing between them, but if you didn't utilize the multi-threading, there wouldn't be any. In order to be able to share an object between different threads, it has to be an object that's not changed. In that case, if the master will create for example, the Geant4 geometry, it's an object that's created by the master, and the workers can refer to it, can obtain information from it without changing it. In that case, it can be shared, only reads. For other things, though, it's not as simple. So at the basic level, the Geant4 geometry and physics is configured before we start extra threads. Then a certain number of per event seeds for the random number generator is generated and put into a queue. Then for each thread or unit that is going to be contributing to the simulation, some initialization is done for what it needs to utilize in running the application, and we'll explain that later. Then it can run through its event loop. It will pick a certain number of these events. There can be competition, can be a round robin fashion, and so on. At the end of this, it could be that it only does one event if you've asked for only for a few events. But at the end, it will finish the run on that worker thread. And in certain cases, if there's information that you've asked Geant4 to store, for example, I mentioned there's the analysis module and histograms are generated, you can automatically have those objects merged in a global run. In addition, it is possible for you to write code with which objects that you create are merged at the end of the simulation. And I will try and explain this in the follow-up presentation, which I believe is on Thursday. We have not gone into this in detail, but in general, Geant4 application has a simple finite state machine. Before it is initialized, it will be simply in the uninitialized state. Once you run initialize, the geometry, the physics and the geometry will initialize. That means that the geometry will create extra information, which is used to optimize and not do unnecessary calculations to find the next volume and so on. And the physics will have created the tables which are required to undertake quick lookup of the cross-section, of the range, or other quantities. When that is done, you start the beam, you start the event simulation running, and eventually, of course, when all the initial events have happened, you are completed. In the case that you're using a multi-threaded application, when the event loop starts, you start a thread which needs to do its own initialization, and there's a small amount of extra initialization which is done for scratchpad information for the geometry. Some information needs to be recached for the physics. Then you run the event loop, and at the end, when each of the workers has done what it needs to do, the event loop, the master will know that the event loop is finished because it will have received information about this, and you will continue to completion. One of the key benefits of having a multi-threaded application is that you're able to save memory compared to running the same application multiple times. So in Geant4, it is possible for threads to share things which are invariant during the event loop. That is, things that would not change, do not depend on what event you are in. So this information will need to be read-only. The key information that this concerns are the geometry definition and the electromagnetic physics tables. The geometry in large setups can take up dozens or maybe even hundreds of megabytes, depending on its complexity, and not just the number of volumes, but also how many volumes are at the same level and how much extra information is generated when voxelizing. Electromagnetic physics tables, if you have just 5 materials, are not going to be a big deal, but in LHC experiments, they have on the order of hundreds of materials. Some of these are even necessary. Maybe 100 to 150 materials might be necessary. Maybe some others could be either exactly the same or could be optimized because they're close enough. But in general, at some point, it doesn't matter. So an application could have several hundred megabytes or a gigabyte of memory requirement. In that case, you can see that sharing this would be quite useful. And of course, even if it's not necessary for the amount of memory, the fact that you're reusing read-only memory means that the caching system of the processor will work better and will provide high performance this way. So data that are stable within the event loop are shared amongst the threads, while data that's transient within the event loop are local. So what is shared by all threads? The geometry, which I just mentioned, the particle definitions. As you've heard, we've had quite a few number of different particles, and the properties of an electron, the properties of a proton, the properties of a particular ion are all constant during the simulation. Cross-section tables, and also user-initialization classes. And we'll go into that a little bit more on Thursday. But if you have a class that your detector construction will not depend on whether it is in different threads. However, it will be called in each thread to do some things. So that the user-initialization classes that you provide will typically be called will typically be one instance. However, they will probably generate things which are utilized in each thread. What is dynamically changed during each event, track and step, are all transient objects. The G4 run, it's a bit more difficult to explain, but we can get back to that why. But certainly an event, the event that you're running on each thread, I mentioned we're doing event parallelism. Thread 1 will have event 1, thread 2, event 2, and later on event 12 and 32 and whatever. Thread 3 will have a different event. All those are different. The track, the current track, the current step, if you're generating trajectories, the hits that you're creating are all going to be different. They're going to be using different areas of memory. What might be less intuitive are that the physics processes there's a C++ object which encapsulate transportation or the multiple scattering. It'll be a different object that will be utilized in each worker thread. The reason for that is simple. The object is created such that when you're starting the step, it will be given information about what is the current values of the track, what's momentum, energy, what type of particle. It has a scratch pad where it writes them in it. So that object will be a different object for each of these threads. In general, that's not a massive overhead. And it allows us to reuse the processes that we created. And if you had to make physics processes thread safe, it would be a lot of extra effort. And you'd have to have this information that you're using as a scratch pad would need to go somewhere else. So this design choice is not something that I would change today, but it's a design choice that was made already around 15 years ago and which remains. Sensitive detectors are objects which are created by you and which manage the hits that are created. Again, these objects need to be per thread. And the user action classes, that is an instance, an object of the class of your stepping action will be created for each thread. An object of the class track action will be created for each thread. Again, because it will have a state. The user-initialization classes that will be used to create them are shared, but the objects that they create should be per thread. So if we look at let's say we had 16 available cores on our machine, and an application that had a fairly complicated geometry or a fair amount of number of materials. In that case, if you look at on the upper half of this slide, without Geant4 multithreading, then the data that would be generated by running the application a number of times, in this case, I guess around 10 times, would take up an amount of memory in your system. And the transient data, which generally needs to be different, would likely not take up anywhere near as much. So you would be constrained by the amount of memory that you have in your system if you want to run it more times. If you're more sophisticated, you can imagine that you can, instead of running it separately more times, you can start it once and fork and have it run more. Have it run a few more times and use the memory reasonably more efficiently. That is a reasonable thing to potentially do, and I believe that at least one of the LHC experiments, I think at least does that, so it doesn't reuse Geant4 multithreading. However, we believe that the model of Geant4 multithreading allows you to save even better than that, and practice has shown that it has improved the efficiency of using the memory a lot more. And by reusing this, you're also using the memory system of a CPU in a better way. The caches are being used in a better way than in this application, and a little bit better than it would be in a multi-process application. So if you just try and rerun the same application multiple times by hand, you will certainly get less performance than you're using Geant4 multithreading. It might be something that you want to do to check your application has been multithreaded correctly, or if you don't have the time to multithread it. But if you're going to be running your application quite a lot, then there's quite a few benefits in running a multi-threaded application, unless you hit some wall or some bug. In the original versions of Geant4 multithreading, in Geant4 10.0, the amount of memory that was required by an application grew rather fast with the number of cores. In this case, we're talking about a processor that is not particularly important today, but since it had on the order of 60 CPUs, and it allowed you to run up to 240 threads on a desktop machine, it was a reasonable way of demonstrating this. The improvements in Geant4 10.1 and 10.2 were such that the amount of memory required was much better. We were able to more objects of cross-sections, I think, were shared, and thus the amount of memory that was required was significantly less. In the two almost vertical lines, or very steep lines, you can see what would be required to run without multithreading, both with Geant4 10.0 and with Geant4 9.6. So a fair amount more memory is required for each of those. Again, although the CPU is not as relevant, the same effect will be seen on more modern CPUs. If you have let's say 8-core machine, you can run with 8 threads, and you should get pretty much linear scaling in your application, unless you're doing something very badly wrong. If you have events that last only a few fractions of a second, a few milliseconds, and then you're reading or writing to a file, for example, if you're writing the random number seed that you have of a current event, then you will not get such scaling. But if your application is running reasonably well, you're running with 10 CPUs, you should get maybe 9.5 times the performance of running with a single CPU. However, once you're already using each CPU, there is some benefit to be obtained by oversubscribing. It depends on the hardware. In this case, you are able to get a substantial benefit, about 30% more for each of the extra threads that you're utilizing, and then it started to fall off. On more modern systems, I don't think there's any benefit to going for a third thread or for a third worker per thread, and you will have to figure it out where you will stop getting benefit. So we mentioned a little bit in general what type of objects are shared and what type of objects are not shared within an application. In what is shared are the geometry objects and the physics tables, whereas the tracks, steps, hits, are not shared by different worker threads. In addition, each Geant4 thread, each Geant4 worker will have its own instance of key Geant4 objects, which we used to call singletons, and we may still call singletons, but it means only one object of these exists per worker. The Geant4 event manager, the tracking manager, the stepping manager, the transportation manager that I mentioned earlier. A field manager really doesn't belong here because you can have one per different type of field, but certainly the field manager for the global field, a navigator, sensor detector manager, and so on. They're all thread local. It is correct to say that every field manager has to be thread local as well. In the user-initialization classes, for example, the G4V user detector construction class, the G4V user physics list, and the G4V user action initialization class, which was introduced for the purposes of multithreading. So saying that it was newly introduced is an old word, but it means it was introduced for multithreading. They are shared between threads. These are the classes, though, that will generate objects which are not shared. So if you have a thread local object and wish to access a shared object, then you can run into trouble. From a detector construction object, you cannot, for example, look at a stepping action object. What you will do is you will create these objects in the user action initialization, and they'll be thread local. In these thread local objects will only be created after the first beam on, as I mentioned earlier on. So you should have a reasonable mind map to what classes are shared and what classes are thread local. So we'll try and give you one. So in a sequential mode, the main of an application will create your run manager. The run manager will create a run. You say run beam on, it'll create an object which is called a run and which encapsulates certain qualities. The run manager will create an event manager, which will go through its local events or its events. An event manager will create a tracking manager, which is the one that picks objects off a stack and says, here, it creates the track and then passes it to stepping manager. And the stepping manager will go step by step, updating the quantities in the step and so on. This was relatively simple, how it worked for about 10 to 20 years, depending on whether you were involved in the prototype versions of multithreading. In the case of having a multi-threaded mode, each worker thread will have its own instance of the worker run manager, an event run manager, a tracking manager, and a stepping manager. The main application will create a particular type of run manager. In this case, the original example, we're taking the original example of Geant4 MT run manager, which creates a run for the master thread. However, that run is really a stub. It will not have objects until you might use it at the end of a run to accumulate things inside it. The first worker thread 0 will have its own worker run manager, which will enable the initialization of everything that it needs to do, to copy from things that were created in the master thread, and will create an object of G4 event manager, which will create an object of G4 tracking manager, and so on and so on. So if you're in thread 2, you do not know that a G4 run of thread 0 exists. You have one object of G4. You have your own worker run manager, you have your own event manager, it has its own stepping manager. In sequential mode, the run manager can have an associated user run action. Write out the random number generator state at the start of your run. Reinitialize histograms, whatever. Things can be done there. The event manager can will need to have a primary generator action and can have an event action, and a stacking action. The tracking manager is the place where you will put things that can be done at the start or at the end of each track. And the stepping manager is the way that you will hook an object which will be called after each step. In the case of a multi-threaded application, there will be, as I said, a run manager in the master thread, and it can have a user run action there. It's not going to do very much. However, each worker run manager will also have a run action, and each event manager will be associated with its own copy of the user primary generator action, of the user event action, if you have one, of the user stacking action, if you have one, and so on and so on. So when an event is happening, it will be talking to a different copy of user run action by the worker run manager, or a different copy of the user stepping action inside the stepping manager. If you create your own user stepping action and you do something like sum up some value, all the energy in a particular part of the detector, which is a quick and dirty way of undertaking some actions, doing some counters, you'll have to understand that these sums need to be brought together at the end of a run. For example, I'm not sure whether, before moving on to more concrete commands and other things, it makes sense to give a chance for questions now.
I don't see any, no matter what.
No. Okay, I guess we continue. So we'll come back to actions that are needed to best adapt an existing application. However, you expect to run your application in multiple threading, you've got it adapted, you're trying to run it. The number of worker threads which will be utilized is one of your key variables. You might sometimes want to run it with a small number, sometimes want to run it with a large number to undertake a large production. There's a few different ways that you can control this. There's a shell environment variable, G4 forced number of threads, which will overwrite alternative settings, and it's a way that you can say how many threads you want to use in your application. It's a quick and dirty way. You don't have to provide an argument to your program, and it will override everything else that you have. You can set it to an integer, or you can set it to the string max, in which case it will use as many worker threads as your CPU is expecting to have. If your CPU is single, each CPU core expects to run only one thread, it will probably use only one thread per core. If it expects to run more, it'll probably use more, typically 2. In the case of you're running interactively, it might also be useful to simply set, if you have a multi-threaded application, to use run number of threads to set the value, or to use maximum number of logical cores. One notes that if you're already started in the middle of a run, you can't change this value. You can only set it when you're before the initialization stage of an application. In the main program of your application, where you have already created a run manager, you can also set the number of threads simply by calling the method run manager set number of threads. But you must do it before you initialize. Once you've initialized, it's no longer possible to do it. On some operating systems, it's also possible to tell threads not to migrate between different cores, so that if there's information that's in the cache of a particular core as you're running, it will not be migrated away. And if you have a fair amount of information like hits and the rest, it would make more. It'll help more. On other operating systems like the Mac, this is not possible. You cannot you cannot pin the affinity, so that your programs will, the work of different threads can be moved to different cores by the operating system without your control. And that's the default in general. If you run with 10 cores, but you're getting an improvement of a factor of 4 or 5 or 3, it might be that your operating system is getting in your way and you might want to test this. It might be that there's something else. I mentioned earlier that typically each thread will take one event and simulate it, and that's what you expect in high energy physics. Events will take seconds, if not tens of seconds. However, if you have a different simulation, if you're looking at a different granularity, if you're looking at a very small detector and its detailed effects, or if your application is from different application area where the amount of energy in a primary set of primary events that you put in a primary particle, in an event, set of primary particles you put in an event is small, then it could be that each event only takes milliseconds or maybe less. In that case, spreading the amount of work by a single event is not going to be efficient. And it's much more important to make sure that each worker picks up and simulates 10, 100, 1,000. There is a default in Geant4 for how you choose to assign this work, but you can override it by providing by running the command in the title of this, which is run event modulo. And you can also choose whether you want to seed it only once, if you seed only the initial event, or whether you want each worker thread to reseed each of these events. Both have different advantages. If you reseed every event, it means that if there was something going wrong with one particular thread, or if you run it between one day and the next day and you expect it to be the same results, and something happened, your core was hit by a cosmic ray and things changed, if you're reseeding it, each event should reproduce exactly what you got the day before. And of course, if you have a bug, that's what you might generally want to run in this mode. If you only seed the first event in a batch of events, then what happens in subsequent events can be different, but it might be a little faster, or there's certainly no reason not to try it if you don't have any other worries. So there's a number of commands in which generally the amount of output that you get from a multi-threaded run, you already, I'm sure, have seen the amount of output that you get from a sequential Geant4 application. So multiplying this by a significant number, if you have a significant number of threads, can be a problem. So we give you the chance to control this. You may already have tried to set verbosity, low verbosity for initialization or other things like that to limit it, but this can also be useful in other ways. You can provide you can tell Geant4 to make sure that Cout and Cr are buffered so that each output of each thread is grouped together. So you will get potentially multiple lines. Otherwise, if you don't do that, it could be that from thread 0, the output will go half the line, and then from thread 1, you will get more output from that line, and so on and so on. It is also possible to ask to get the output only from a single thread. It might be for the purposes of debugging. It might be just for the purposes of saying, I'm already writing everything I need. I'd just like to see what's happening in other buffers. I'm recording the information, but let me see what one of these threads does as we're running. Or you might be debugging and trying to understand what is happening in a program. In a multi-threaded application, you will generally see output that says G4 MT and the number of the thread before it. But if you want to do something custom, you can do that as well. Or you can provide a file name for the output of Cout or Cr using the final commands, control Cout set Cout file, or control Cout set air file, and whether or not to append. The file name will have a prefix where you provide G4 worker underscore n, where n is the thread ID. And you can change it for each run. If append is false, then the file will be overwritten. So don't use the same directory and expect the files not as existed before to remain where they are. And when you want to change the output of CR and Cout or CR back to the screen, you can specify the special keyword **screen ** as the file name, and it'll give you the ability to do this back again. In general, if you run a multi-threaded application and you don't understand what's happening, you have a problem, then reduce the number of threads that you're running it on, or try to have the same application run in sequential mode and see if the problem happens. It might take you longer, but it's easier to debug a problem in sequential mode. If the problem is a problem of your multi-threaded code, of course, just try and bring it down to 2 threads and try and figure out and manage it, maybe print out some more information. I've mentioned until now the Geant4 multi-threading, but since Geant4 10.7, a different way of utilizing many cores, but of talking about it or building up the application, the Geant4 internal level exists, which is instead of talking about the threads, you talk about creating tasks, and the operating system or your or another library will assign them to different threads. And it's a different way of thinking about it, but at the end of the day, the same things will be done. In Geant4, the task there's a native way of undertaking this using C++, modern C++, and there's also the ability to do it using the Intel thread building blocks, which is called TBB task mode. So this was introduced now, and it's reasonably mature. It was introduced 5 or 6 years ago. And it's possible to choose at runtime which you will utilize using what's called the G4 Run Manager Factory. You probably have seen it now in basic applications, and I think in most applications utilize it. And you can select either by using an enum with the value default, serial MT, tasking, or TBB, and asking the run manager to create one this way, or by using one of the strings below. So this has been already reasonably mature since almost 5 years. You will see the main application utilizing it. I'm not aware of any massive differences in performance or otherwise between threads and tasks. It is a choice that depends mostly on your external constraints. If you're with an experiment which uses TBB for parallelization, then you'd probably choose that because then you need to choose that because it really meshes with what you're doing already. If you're a user in a small experiment that doesn't have any constraints, you might use a new task mode, or you might choose to just use Geant4 multithreading. In an application that doesn't have external constraints, it should not make a significant difference. Okay, I think that was it.
I think there was a question. So Emmanuel is asking, multithreading runs on what? MPI, OpenMP, any CERN developed alternative?
So multithreading, the original version of multithreading used pthreads, which is a library that was created and was utilized quite widely for the purposes of multithreading. It is not OpenMP, it is not MPI, but it's utilized on a single machine for running applications that can use multiple threads. Since then, our tasking model runs on top of C++ native threading. There has been an option for some time to use MPI, which would of course be more interesting for machines that have multiple actual separated distributed memory. I'm not sure that at the current status.
Yeah,
it still exists and it's in there.
Yeah.
I think it would be relatively complicated to have an application that uses both MPI and these C++ threads, but it might be for someone who's wanting massive amounts of computation, it might be something that's relevant to try and utilize.
Yeah, and still Emmanuel is asking if it is better to have more cores or higher frequency, and does Geant4 multithread support GPUs, or does it have any project to give it?
So on the question is it better to have more cores or higher frequency? The answer is yes. Yes, it's better to have more cores. Yes, it's better to have higher frequency. It really depends how your CPU adapts, what its thermal loads and otherwise. But in general, if you're wanting to only get one result, if you only want to run one event, higher frequency is the biggest deal. If you want to run many events, as you do in almost absolutely every application for particle transport, what matters is the total number of events that you can run. So high frequency most of the time will not matter as much as being able simply having higher multi-threaded performance. And you will see on CPUs on the reviews of systems nowadays that people will talk about multi-core performance and will use multi-core benchmarks. How much you're able to run in multi-core matters more than just the number of count or the count of the cores or the frequency. But in general, having increased each more cores and higher frequency is better. But you could get a machine that's 20 years old that runs at 4 megahertz and one of today's machines that runs at 2 megahertz and still today's machine would outperform it because it does more per CPU clock cycle. Then Geant4 today, as you have been provided, it does not support GPUs. However, there are, I would call them somewhere between R&D projects and getting close to being used for meaningful applications. Adapt is one that has been developed primarily at CERN. There's a project called Celeritas, which is an R&D project in the US. We have slightly overlapping and slightly different goals. Adapt is being evaluated by several of the LHC experiments and has shown promising results for the parallel shower development of electrons, gammas, and positrons for full production, for the full production setup. So it's not, you're not using it for a toy part of, you're using it for realistic applications, but it's not that it's going to be used in realistic applications next year, but it looks promising within a few years' time. And certainly we think and hope that it will be brought up, that it'll be embraced by these experiments, and as such, it will be brought into production in the near future. Celeritas has originally had the same targets, but has actually focused more on optical photons and other applications which are outside the core interests at the moment for Adept. It brought many other interesting concepts and shared a lot of the underlying ideas, and there was a significant sharing of ideas. But I think at the moment, the more promising one for applications in large experiments is Adept.
Yeah, there is another question from Julian. If a program has been adapted to run in either sequential or multi-threaded mode, if selected, can this choice be made from an external input file read by a custom function?
Basically, you can, of course, write a main application which takes a string like multi-threaded, or takes a string like here default or TBB or task or whatever it is, and choose at runtime whether you will run in sequential mode or in multi-threaded mode. It's up to you and how you write your application. So, of course, to do that, you need to have an installation which has been created so that Geant4 multithreading is enabled, and a system which has a library which will enable it. But I'm not aware of any modern system that doesn't. It's just that if you have an installation of Geant4 in which the person who created the installation chose not to have a multi-threaded version of Geant4, you won't have that choice. If you do, you can take any Geant4 example and put an if statement, or have it read a file, whether the file says default or serial or MT, do something different, or it can be a flag. So you can certainly do it at runtime. We have a local question.
You mentioned that we can set the number of worker threads, excluding the master thread. So should we reserve a CPU core for the master thread, or it's not needed because it doesn't really run any events?
It typically will not be necessary. The only reason that you might be necessary is if you have massive amount of data that is being output by your simulation and you want to merge it. But even then, I think that's not a very typical situation, except if you're running the machine interactively. If you have a machine that has 4 cores and you want to use it interactively for doing this or that or the other, and you run it with, say, 5 threads, 7 threads, you probably will not get very good use out of it while you're running it like that.
Okay, thanks. And I have another question related to just what you mentioned, that how we can thread safely trigger dumping data from the master thread into output file regularly during the run, and not just the end of the run. How is it possible?
It is possible to coordinate how you use a particular resource. For example, an output thing. It's not easy. If it is important for CPU purposes, then it's not something that would require rather complicated things. If it's unimportant for CPU purposes, then there's a way that you can add it. You can add you have to synchronize when you're using an external resource. So you'd probably look at a Geant4 class that does it. For example, the one that comes to my mind is G4 Geometry Manager, and a couple of classes that you will see. You have to create a mutex, and then say allow only one thread to be in a particular part of code. When you open a file, you have a method that opens it and blocks it, and then when you finish your action, you can close that file and move on, or something similar. It's something that you have to program by yourself. It's not something that's automatically done within a run.
So you mean triggering the dumping of data from a worker thread?
If you have separate, if each worker thread dumps data into a separate file, you don't have anything to worry about it. If you want to dump it into the same file, then you have to synchronize it.
Okay, thanks.
I think this applies also for histograms, but for histograms, there are already tools that allow to do that in a thread-safe mode.
For histograms, okay, you might be interested to do this in order to get a running total. Maybe our next speaker will know whether there's an example that shows something like this. Makoto is online. I do not recall one off the top of my head.
Okay, I think we have completed.
Okay, yeah, actually, let me comment on a few things before I start my own. The one thing is MPI is still functioning very well, and I do aware of the users who use both MPI and multithreading. It's
the brave users.
Yeah, experienced users, I must say.
Ah, okay.
Yes. And about the runtime choice of the run manager mode, there's an environment variable you can set, G4 run manager type, so that by setting that variable, environment variable, default serial MT tasking TBB, you can really switch on the fly.
Thank you. Okay, let's